We are Transformers Racing, and this is our design brief for the 2024 to 2025 Energy Invitational.
Through participation in this competition, we aim to produce an improved car that is cost-effective, at least 30% less than its weight from last year, and energy efficient, all under a budget of $1,200. Through this process, we also want to nurture our engineering, research, and critical thinking skills as we assemble and design a vehicle. This is our advisor, Mr. Berger, who oversees the engineering CTE pathway at our school.
This is our team. I'm Laura, and I'm the product manager. And here are some of our roles and responsibilities, such as Sang, who is responsible for the chassis, Kiro for the electrical, Alan for the steering, Nathan, who is our driver, V for safety, and Teresa for rolling assembly. We also have some leads that includes Nathan, V, Teresa, and myself. This is a timeline of important dates, key milestones, and important tasks, such as the creation of our design presentation, the design and CADing of our chassis, the assembly of our go-kart body, and also when we should be finished with the whole assembly.
For our basic vehicle configuration, as a school, we chose to implement a universal template in which we all contributed in making. The materials used will be machine cut, welded, and put together in the workshop at Westminster High School. Almost the entire cart will be custom built aside from the motor system and safety gear. Attached is the CAD of our design, which took into account the maximum weight of the vehicle as stated in the new rulebook for 2025, the fact that the maximum weight with batteries is to be 100 kilograms. All of the configurations and measurements correlate to which the driver to make sure that they are both snug and ergonomically comfortable inside the vehicle while keeping a low weight for efficiency.
Our powertrain configuration will consist of a 1-inch steel rear axle connected to 16-inch diameter bicycle wheels. Our vehicle will be powered by two 12-volt batteries linked in a series, adding up to 24 volts. A chain drive will be linked to the motor sprocket and a 75-tooth axle sprocket. This is the largest axle sprocket we could find that could fit our vehicle, which leads to a higher gear ratio and thus better fuel economy as our vehicle can maintain speed with less effort.
We will be using a Cycle Analyst V3.1 from Grid Technologies to monitor key logistics such as speed and energy consumption in a vehicle. A standalone shunt will be installed between the battery terminals to measure current and voltage, providing data to the analyst. The Cycle Analyst will be wired to the motor controller via the throttle output to regulate power efficiently. We will be using a hydraulic brake system mounted on the steering wheel / handbar to ensure efficient and responsive braking. The system includes front brakes operated by two levers, providing precise control. A disc brake mechanism will be implemented where a caliper clamp onto a brake disc attached to the rear axle to slow down the vehicle. Through research, we found that this disc brake system is a common, cost-efficient, and reliable method for steering and stopping.
Our suspension system uses static suspension, meaning that the suspension components depend on the vehicle's frame and durability. Since the racing terrain will be relatively flat, this deters implementing a complex suspension system, saving us both weight and time. Our vehicle will use the Ackerman steering system, common in numerous go-karts. The inner wheel will turn at a greater angle than the outer, traveling a shorter distance, which should prevent the tires from slipping during a turn. The steering system parts consist of spindles, tie rods, steering knuckles, a steering column, and a steering wheel. The assembly will be relatively simple, fastening the components through nuts and screws. With dependent suspension, the wheels on the axle will be connected by a solid beam. We decided to use this suspension system because it is more economically feasible and simple to manufacture.
In today's day and age, everything is documented on social media, and we hope to share everything from our challenges to our engineering breakthroughs through such platforms. We utilize Instagram as our social media platform, which facilitates our ability to raise funds for our team. For example, on our Instagram page, we linked a GoFundMe which shares our story in order to help us generate funds for things like t-shirts, showing our involvement within the program.
Our safety intends on keeping both the vehicle and driver safe. Our vehicle, we will enforce a bumper that has sufficient crumple zones that absorbs most of the impact by using foam materials. The vehicle will also contain mirrors, insulation rubber for any electrical wiring, wrist restraint, and a 5-point harness to safely secure the driver. Our driver will wear a helmet, fitted neck brace, full body tracksuit, and gloves.
After going through the Vital Link EV Challenge booklet, we noticed some new rules for 2025, like how the main restriction for a 24-volt nominal drivetrain and battery pack remains the same, and that the allowed voltage for a fully charged battery pack is 29.4 volts. For the vehicle weight, unlike past years where there was a maximum combined weight of the vehicle and the driver being 300 pounds, new rules state that the maximum weight of the vehicle with batteries is 100 kilograms, which correlates or translates to around 220 pounds, with there being no minimum weight. For the brakes, we were definitely one of the teams who had a rough time locking the front wheels when applying the brakes, so that the new rules state that it still applies and a rear brake may be used. But for our 3-wheeled car, we must have brakes that lock up the front wheels. And to maximize preparation for tech inspection coming up later on, we are going to go through each item in the handheld checklist to make sure that everything we do from brake calibration to assembling all electrical elements follow the stated rules.
Currently, our biggest challenge is the split of members across different classes. Since the majority of students are in the first-year engineering class, it makes working on vehicle and communicating about changes much more difficult as our second years are in a different class. Furthermore, our extensive schedule makes it difficult for all members to participate after school on our vehicle.